So we're about to begin lecture 6. Thank you, everybody, those of you here for staying. I know it's difficult on a test day, but you've done your test. You can relax. And we're going to be revisiting some of the things we've seen in the last 2 weeks, but also do a bit more on them, extend them. So I like the little thing James has put at the start of this lecture. We are going to be looking at expanding binomials, expressions like that, a plus b to the n, but we're not going to do it in that way because that's a load of rubbish. So we're going to look at, we're going to relook at inclusion, exclusion, we'll be seeing those binomial coefficients again. So we're still doing some counting. Okay, now we're going to do some expanding, and I'm going to scribble on this in a moment. Where's it gone? Oh, yes, and I have some, remind me, I think we might need some Easter eggs partway through this. You know how to expand the first one of these, x plus y squared. You did that at school, right? And most of you might go straight to the answer. You can expand it out in several steps or go straight to the answer. And then when you do the next one, it's probably good to do that in steps. You've just got x plus y all squared. So you can write that there and then multiply it by x plus y and tidy it up and get the answer. And then, because you're having so much fun, you can do x plus y to the 4th. Do we fit x plus y to the 5th? And that's all there is room for. So on the next slide here, we have a whole lot, one more of these. There's a bit of a pattern here. There's a Pascal's triangle. Have you seen those numbers before, the numbers that appear as coefficients? You have. They're the numbers which do look familiar because there's just the numbers there. We saw them last week with Pascal's triangle. So I'm going to start scribbling. It's all very nice to watch it there, but I can't scribble on the wall. And I want to scribble. So, in general, that's the pattern we're seeing. We've got all the possibilities of powers of x and y where the exponents add up to n. And you might like to go back a couple of slides. Let's just pull this one back for a moment. Where has it gone? There. Let's look, for example, at the x plus y to the 5th. You've got your x to the 5th, your y to the 5th, and then you've got every other possibility of x's and y's where the exponents, because it's the 5th here, in each case they add up to 5. That y is y to the 1, 4 plus 1 is 5, 3 plus 2 is 5, that's 5. 1 plus 4 is 5, and that's 5. Same with n. The exponents all add up to 5, and then you've got these various numbers in front. That's a 1. That's a 1 because x to the 5th is just 1x to the 5th. So that's really what that's saying. Now that looks a little untidier just because it's in general. But you see that in each case, your exponents add up to n and you've got a number in front. But what this is saying is that you know the coefficient. The coefficient is something we've seen before. They're the binomial coefficients, which are the coefficients in this binomial because that's a binomial. Okay. So you could work out x plus y all cubed as on the earlier slide, or you could just use the binomial theorem and say, well, we've got all these terms. We start with I equals 1, and that's x to the 0. Oh, that means x just disappears. Y cubed, there's our y cubed, and 3 choose 0 is 1, and so on for each term. And sometimes that's the way you want to go. I mean, it's all very well to multiply out x plus y all to the power of 20, but I reckon this is easier. But is it true? We saw something, ooh, that's still a bit, that's better. Now, you know I make mistakes and I say things that are rubbish. And maybe James even writes things that are rubbish on the slides, but not often. But maybe, you know, that theorem's not true. So maybe you actually want to know why it's true and be convinced. You would like to be convinced, wouldn't you? Yeah. Good. Thank you for those of you who nod. I saw some of you nodding. Oh, that's lovely. I saw a couple of people nodding. I know several of you did, but thank you. I like some positivity there. That's good. So, actually, I couldn't see many proofs in Wikipedia, but there's a proof by induction there in Wikipedia, which later on, at the end of semester, you'll know about proofs by induction. I'm pretty sure we're doing induction. Love induction. Anyway, what we're going to do is a counting argument. Well, we know what x plus y to the n is. It means multiply a whole lot of these together where there are n factors. There's n of them. That's what x plus y to the n means. There's n of those and they're all multiplied together. Now, let's just think about what happens when we multiply this out. When you multiply it out, you've basically got one of these times one of these times one of these, etc. Each and every possibility. You'll end up with x times x times x, etc. X all multiplied together. That gives you the x to the n. You'll have y times y times y, y. That'll give you the y to the n. And then you might have, you know, x, y, x, y, x. And you'll get all possibilities of x's and y's where you've taken one from each factor. That means you've got n of these things in total. So if you've got I x's, you'll have n minus I y's. But you'll see some of these a lot. Because I can go x, y, x, or I can go y, x, or x, y, x. And I'll see x to the n minus 1, y, a lot of times. How many times? Oh, that's a counting problem. So when we tidy everything up, we'll have a whole lot of those, and we'll have to work out how many. Okay, how often do I see the term x to the I, y to the n minus 1? Well, I get that whenever from I of these factors, I choose an x, and then from the others, I choose a y. I have to take a y. So in how many ways can I choose I of these factors to take an x? I'm choosing I things from n. In how many ways can I choose I things and choose I? And choose, yes, that's the way around. It's n choose I. Now, if that doesn't make sense to you, I suggest you at home think about multiplying out just the 3 case, the x plus y, x plus y, x plus y, or maybe even x plus y squared. But that's the number of ways in which we can get the term x to the I, y to the n minus 1 by multiplying this out. Because when you multiply things out, you've got to multiply every possibility. Think about that when you multiply 2. Think about that when you multiply 3, what you're actually doing. So you see x to the I, y to the n minus I, n choose I times. And that's it. The coefficient of this is n choose I. And that's it. That's the proof. You can do it with just a simple counting argument. That is lovely, isn't it?
Yeah.
It is. Oh, I heard a yes from over there. I mean, I know a lot of you said yes, but I just caught your voice there. I just heard it. Okay. So that's nice. Now, if you're not happy with that proof, you might like to wait till we do yes.
So does that mean that Pascal's triangle numbers reflect n choose I?
Yes, that we showed last week. Yes, 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 it does. And that's a good point. Actually, I should pause for a moment because I don't think that's on the pictures there. Yeah. So let me show you on I've got a spare piece of paper here. That's a very good point taken aside there. So if I'm multiplying, if I want to do x plus y to the 6th, say I want to write that out, and this is how I actually do this. I know that the coefficients here with the binomial theorem are the n choose I, and I know Pascal's triangle gives me n choose I. Remember Pascal's triangle, we put 1s down the side. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 1, 1, 1 plus 4 is 5, 10, 10, 5, 1, 6, 15, 10 plus 10 is 20, 10 plus 5 is 15, 6, 1. Okay, and that gives me the coefficients in the expansion of x plus y to the 6th. So I can write it out immediately. It's x to the 6th plus 6 x to the 5th y plus 15 x to the 4th y squared plus, you see the long part, the thing that takes the time is actually writing it out. Nothing else. I mean, everything else is so fast that it essentially takes no time at all. X squared y to the 4th plus 6 x y to the 5th plus y to the 6th. See, what actually took the time, the slowest part of this was actually writing out the answer. Working out the coefficients was really fast, wasn't it? There's such a nice way of doing it. Thank you for asking that question. That was a good one. Reminded me of something good. By the way, if you're closer to the front, you're more likely to get an egg because I don't feel like running right up the back. Maybe I will, but
How's it going now?
pretty bad. My aim is terrible. My throwing arm's okay, but my aim is shocking. I don't want to hit you all in the head or something like that. That would not be nice. Okay, let's do something that makes us think a little bit about the binomial theorem. Let me bring the binomial theorem back here. And I'm going to, there's a binomial theorem. It's there. There's the whole thing. I'm actually not going to, I'll probably do it. Why not? Got a piece of paper here. Might as well use a piece of blank paper. Expand 3x minus 5y to the 5th. You can do that the long way, but I just showed you that using the binomial theorem and Pascal's triangle is really fast. We're going to do it the really fast way. In fact, we happen to have on the back Pascal's triangle. These are the numbers we're going to use because it's the 5th power. 1, 5, 10, 10, 5, 1. And the binomial theorem says that this is equal to sum from I equals 0 to n of n, which is 5. Oops, n is 5 in this case. N equals 5. N choose I. Now, it's not x plus y here, it's 3x plus minus 5y. Okay, so it's a little more complicated than x plus y. Instead of x, we've got 3x. So I'll put 3x, all in brackets, to the I. And instead of y, I've got minus 5y, which I'll put all in brackets. and that's 5 minus I. Okay, so you see what we did there?
Did you replace the and inside the coefficient binomial coefficient?
I actually should have done that. Thank you, because it won't help us if we don't do that. Probably owe you another egg for that, but you've just had one. Okay, so you can now write that out. Well, I'm going to, we've used the binomial theorem. Thank you, binomial theorem. I'm going to pick out of that the term with x squared y cubed and find its coefficient. I mean, I could do that. Actually, I'll start writing out the whole thing. I'll leave you to finish it. I equals 0. I equals 0. 5 choose 0. That's actually 1, but it's 5 choose 0. 3x to the 0. Oh, that's just 1, isn't it? So I'll leave that out. And then we've got minus 5y to the 5 plus. Okay, and we keep on going. All right, I'm bored. I'm going to work out the coefficient of x squared y cubed. I'm going to get, so we're looking for the number in front of x squared y cubed. One of these terms gives us an x squared y cubed, doesn't it? When I equals 2, so the term with I equals 2. I've chosen that because if I is 2, I'm going to get an x squared there. I'm going to get other stuff, but I'm going to get an x squared. And I'm looking for something with an x squared y cubed. And if it's 2, I'll also get my y cubed. So the whole term will be 5 choose 2 because I is 2, 3x squared minus 5y to the 5 minus 2 cubed. Let's tidy that up. 5 choose 2. Pascal's triangle. That's 5 choose 0, 5 choose 1. 5 choose 2 is 10. That's 10 times 3x all squared. 3 squared is 9, and then I get the x squared. Minus 5y cubed, it's minus 5 cubed. That's minus 125 times y cubed. Let's tidy that up a bit. Equals, it's all negative. I don't know, what's 90 times 125? I don't know. 11,750. Oh, 11,750. That's right, is it? I'll just put x squared y cubed. I'm trusting you on that one. That looks good. It looks right, doesn't it? 90. No, that's not right.
No, it's 11,250.
250, thank you. All right, I knew it was wrong because it was wrong modulo 9. That's something we might talk about later. Okay, 11,200, that looks right. Are you all happy with that? That correct? Thank you. Okay, we got there. So what's the answer, the coefficient? What is the coefficient? The coefficient is minus 11,250. Or you could write it as minus 10 times 9 times 125. Okay. Happy? Okay, so you could continue that and write out the rest of the expansion, couldn't you? Term by term. I mean, we did the first term, that was easy, and I did one particular one there, and that wasn't too hard, and the rest are no harder than that. Leave it to you. And if you're not sure, and if you've got an answer and you want to check it, you can always email me. Thank you to those who emailed me last week. I'm feeling slightly loved, because a few of you emailed me. Okay, Pascal's triangle again, exercise. Now, we talked about this. I mentioned this because this is so much fun. Last week, it says, write down a few rows of Pascal's triangle, calculate the sum of each row, and we did that last time. We got That's 1. 1 plus 1 is 2. That's 4. That's 8. That's 16. That's 32. That's 64. That's equal to 2 to the 0. That's 2 to the 1. That's 2 squared. That's 2 cubed. That's 2 to the 4th. That's 2 to the 5th. That's 2 to the 6th. That's what happens when you add up all the numbers. There's a pattern there, isn't there? Okay. Can we prove it? There's a hint. Let me show you. It's once you've seen it, you'll love it. You'll love it. Okay, make a conjecture and prove it. Okay, here it is. I think I can fit it in here. I'm going to use the binomial theorem. So I'm going to use the binomial theorem. And I'm going to expand 1 plus 1 to the n. I'm using the binomial theorem with x equals y equals 1. I can do that, can't I? I can replace x and y with 1, can I?
Yes.
Of course I can, yes. Okay, so that equals, let's just skip to this way. It's n choose 0, okay, 1 to the 0 times 1. If as x and y are both 1, that term, it's just times 1, isn't it? So you don't see that. Plus n choose 1 times 1 times 1, plus n choose 2 times 1 times 1, plus dot, 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 all the way up to n choose n times 1 times 1. There it is. But 1 plus 1 is 2, so 2 to the n equals n choose 0 plus n choose 1 plus all the way up to n choose n, and that is the nth row of Pascal's triangle, isn't it? Which is I've only got a few pieces of right. So I'll call that that's the where we do say the 5th power. That's with the 5. That's the row. I'll just say which is the sum of a row. Of Pascal's triangle. All right. So that's the proof. The binomial theorem does that. What if we took the alternating sum? Add, subtract, add, subtract, add, subtract. All right, where's my black pen? I'll scribble over this. Over this side, all right, I'm going to put that away for now. And say 1 minus 1 is 0. 1 minus 2 plus 1 is 0. 1 minus 3 plus 3 minus 1 is 0. 1 minus 4 plus 6 minus 4 plus 1 is 0. Oh, the first one's different. But it looks like apart from the first row, we might be getting 0. Is there a pattern there? Yeah, it's 0, 0, 0, 0, 0. How might we prove that?
Inside brackets 1 minus 1 to the power of n.
Brilliant, brilliant, brilliant. Yes, binomial theorem with x is 1 and y is minus 1. Yes. So apart from the top of the triangle, where we only get one term, the sum is 0. And to prove it, expand 1 plus minus 1 to the n, because 1 plus minus 1 is 0, and 0 equals, and you'll see when you write that out with the binomial theorem, you get an alternating sum, and you might like to play with that. It makes you think about, it makes you rewrite the binomial theorem. It's really easy to put ones and minus ones in here. The ones disappear and the minus ones change sign, and you might like to think that. If it's a little bit hard with the too many, the n's and so on, do it for 3 there or 4 there. Play around with it. It'll get you used to the binomial theorem, and you'll have some fun. You can play with Pascal's triangle, and you'll learn all sorts of things. Okay, that's not all you can do with Pascal's triangle, but those are the two obvious ones. Okay, that's fun.
There's also a thing in there. It's no coincidence, right, that it's to the n for the sum of the rows, which is also the cardinality of the power set. Is that a coincidence, or is there a connection somewhere?
There probably is. You can probably find a connect. Yes, there is. Yes. Because if you look at the number of subsets of the various sizes in the power set and add them up, you're adding up the binomial coefficients, and therefore you get 2 to the n. So yes, if you add up the number of subsets of a set, which is all the sets in the power set, instead of just summing up the total, you do it by the sets of size 0, the sets of size 1 and 2 and 3 on, you get exactly that. In fact, that's a nice question. There's a lovely question I like setting, which is very close to something about power sets. I had a lot of fun one time. I set it to a group of about a dozen people, and I got 5 different correct proofs. It's often around that sort of thing. It's very close to that. Okay. We will briefly revisit inclusion-exclusion. Actually, we're going to take it further. Now, here's our old friend inclusion-exclusion, where let's just think about what this says. That's the inclusion-exclusion. And we're going to do this in terms of colours. That's supposed to be red. It looks like a sick red to me, but never mind, we'll call it red. Okay. The number of elements in A is the number of elements in the red region plus the number of elements in the pink region, red plus pink. Then when we add to it the number of elements in B, we're counting up the number of elements in the blue region and counting the number of elements in the pink region again. So the cardinality of A plus the cardinality of B is the cardinality of this set here plus this set there plus twice the cardinality of the intersection. We've counted everything in the intersection twice. Okay, the intersection is just the pink region. The cardinality of A intersect B is just the cardinality of this pink bit here. So when we take this minus this, cardinality of A plus cardinality of B minus the cardinality of the intersection, we get the cardinality of the red region plus the blue plus 2 times the pink, and then we subtract off the number of things in the pink, so it means we get pink once. We've counted the number of things in there appears once, and that is just the red, the blue, the pink. If you add up the numbers in those regions, it's A union B. That's the proof by colours.
Why is it plus pink? It's red plus blue plus pink.
Right, it's because when I take that plus that minus that, we've got 2 times the number of things in the pink, and then we subtract the number of things in the pink. So it's like 2 pink minus 1 pink equals 1 pink. Algebra with colours. Now we go to more colours. Can you see the yellow? Oh yeah, it comes out better on there than it does on the printout. 3 sets. Wait until we do 8 sets. Okay, 3 sets. Let's do exactly the same thing. James has managed to find enough colours to colour all the various subsets you get when you consider 3 sets and the possible ways in which they can overlap. They're all there. 1, 2, 3, 4, 5, 6, 7, all 7 regions and a colour for each of them. And he's worked out these various things. Okay, the cardinality of A, well, that's the number of things in the red region plus the number in the pink plus the grey plus the yellow. So there it is. The red, 1 lot of pink, 1 lot of grey and 1 lot of yellow. But then if we're going to add the number of things in blue, we've got, in B, sorry, the whole set B, we've got the number of things in blue, the number of things in the pink region, plus the number of things in the grey region, plus the number of things in the blue, in the light blue region. So we've got the blue plus another pink. We've counted those in the grey again, and now we've got the light blue. And then we do the same for counting the number of elements in C. That's the number of elements there, plus the number there, plus the number there, plus the number there. So we get the number in the green region, plus the number in the yellow region again, plus the number in the grey region again, plus the number in the blue region again. So you see, we've counted the elements in the pink, yellow and blue region, we've seen twice, counted them twice. And in the grey region, we've counted it 3 times. Okay, next, let's consider the intersections. What happens if we look at the 3 ways in which the 2 sets can intersect? What are the cardinalities there? A intersect B is the pink and the grey region. So if the cardinality of A intersect B is the cardinality of the pink plus the cardinality of the grey. So we've got the pink and the grey. When we do A intersect C, we get yellow and grey. B intersects C, we get blue and grey. So when we add up these 3 cardinalities, we've got the number of elements in the pink region, the number in the yellow region, the number in the blue region, plus 3 times the number in the grey region. So the grey region is just A intersect B intersect C. It's the intersection of the 3. Okay, now putting this all together, if we take the cardinality of the sets themselves minus the intersection, we're taking minus the intersection of all this, where we intersect pairs, plus the intersection of the 3 of them, we end up with, and that's the way you end up. Let's check the grey, for example. We had, that got us 3 lots of, we counted this number 3 times the number in the grey region. Then we subtracted off that, which means we subtracted 3 times the number in the grey region, and then we added the grey back. Yes, question?
So again, that's adding grey because we've got 3 greys that we've just added 2 of them.
We've got 3 greys here, then we subtracted off 3 grey, and then we added it again.
Why do we add it again, however, if we're looking for... Because we want it once, don't we? Yeah.
That's what we're aiming for. We're aiming to get everything once, because what we want at the end is just the union.
Yeah, we don't exclude grey.
Yeah, we want it. Yep. Yep. Let's check yellow. The number of things here, yellow, that they're counted twice in this bit. They're counted once here. So when we subtract that off, we'd counted it twice, we'd subtracted it off, so we end up counting the yellow region once. And the same for all the others. We ended up counting them once. So that's inclusion, exclusion for 3 sets. Colourful algebra. Make sense? This is not the only way of proving this. You can use inclusion, exclusion with 2 sets twice. You can take A union B union C. B union C, if you've already applied inclusion, exclusion to that, you can take the union with that, and I think you know enough to be able to tidy it up that way as well. Okay, but this is much prettier. That's inclusion, exclusion for 3 sets. And the summary is, the short version is there, and it's easy to remember. You take the sets themselves and add up the cardinalities. You take the pairs and you subtract the cardinalities of those. And then you take the threes and you add those. And that continues, that pattern continues for 4 sets, 5 sets, 6 sets, 453 sets, and so on. Now, I've got a piece of paper here. Wow. Let's do this exercise. I would like to note when you look at the Venn diagram for 3 sets, in fact I might draw in that Venn diagram there, why not, that you've got, for the whole thing, you've got 8 regions. You've got 1, 2, 3, 4, 5, 6, 7, which are within A union B union C. And then you've got another region here, which represents the elements which are not in any of those sets. So you've got all sorts of possibilities when you've got 3 sets. And you can see that in this example, where you've got only 15 people. But you're looking at the various languages they can speak. A person could speak all 3 languages, or none of the languages, or 2 of them, or 1. There are so many possibilities. Oh, there are 8 possibilities, aren't there? If speaking Mandarin, 2 possibilities, do or don't. Speaking Japanese, 2 possibilities, do or don't. Speaking Arabic, 2 possibilities, do or don't. 2 times 2 times 2 is 8. 8 possibilities overall, aren't there? And there are 8 regions here, which one to represent each of those possibilities. Okay, let's start looking at this exercise and see what we can do. How many people speak none of the languages? Well, this region here represents the answer, doesn't it? If you've got A for the people who speak Arabic, I'm going to change that to M for the Mandarin speakers and J for the Japanese speakers. There I'm editing our lovely, pretty diagram. Okay. You happy for me to scribble on that diagram? Okay. And the set of people who aren't in any of those circles is the set who speak none of the languages. So, what's our answer? Our answer is the number of people in total, which is 15, minus those in there. Minus M union J union A. There's 15 people altogether. Some of them are in here. I don't know how many. We might find there's 10. We'll work it out. And that would mean that there'd be 5 out here, and that would be our answer. But we've got to check. Maybe it's not 10. Do you agree that that's the answer? Okay. So let's find out the people in here. That's those who speak at least one of those languages. And the others speak none of them. Well, we know that the order of, or cardinality of M is 8. The cardinality of J is 7. The cardinality of A is 5. Actually, I should start this by writing up properly. Let M be the set of people who speak Mandarin, and I should do the same for let J, Japanese, and A, Arabic. If I'm going to use notation, I should say what it is. Okay. What is 4? What set represents those who speak Mandarin and Japanese? The intersection, yes, the intersection. You said that, did you? Yes, have an egg. I don't want any eggs left over, by the way. I shouldn't eat dairy eggs. So you've all got to help me with these eggs. M intersect J equals 4. What does this tell us? M intersect A equals 2. I've given you an egg, haven't I? No. Oh, well, you've got to have an egg then. You've just got to have an egg. Okay, and this one is J intersect A equals 2, and 1 speaks all 3. That's M intersect J intersect A equals 1. Okay, so we can find out the this here, and I think I'm going to have to move on to this piece of paper where we've got a bit of room. Oh, you could probably do this yourselves, couldn't you? Do you want to do it? Do you want to finish it here now? Finish it? Yep. 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 Okay. All right, we'll do it. Everyone wants to do it. M union J union A equals M plus J plus A minus the intersections, M intersect J minus M intersect, that's an intersect A minus J intersect A plus the intersection of the 3. Okay. And as we go, we're going to record things on the diagram too, because the Venn diagram gives us some information. Oh, there's something I can write here. Look, there's one person there. The grey region has only one person in it, so I'll write 1 there, because there's only one person who speaks all 3. Okay. Cardinality of M is 8, plus cardinality of J, that's 7, plus cardinality of A, that's 5, minus M intersect J has cardinality 4, minus that one 2, minus 2, plus 1. Okay, what's that equal to? What is it?
13.
All right, who said 13? That was, you've already got one. Did anybody else manage to get 13? Oh, you're leaving, so you don't get an egg. See you next week. You can have an egg. All right. Okay. So that's 13 people. So our answer is 15 minus 13 equals 2. So there's 2 people in that region. But while we're here, let's just note that we can do this all on the diagram, because the diagram, it sort of contains all this information anyway. Let's look at it. 2 people speak Japanese and Arabic. Japanese and Arabic, that's that section there. If there's 2 people in there, we know one's there, then one's there. There's one person who speaks Japanese and Arabic but doesn't speak Mandarin. So we can actually work out, let's continue and do this for some of these regions, Arabic and Mandarin. Arabic and Mandarin, 2 speakers. Okay, so there's 2 people there in total. One's there, so the other one must be there. Arabic, we've got 5 Arabic speakers. So we've got 1, 2, 3. If the total's 5, then there must be 2 speakers in that region there. So you see, we can find out the cardinalities of every single region represented on that piece of paper. Okay? So we can do this by diagram, we can do this by formula. You can do this by thinking. All right. So that's fun with colours and sets. You can go home and tell everybody that you played colouring in diagrams again today at university. They'll be impressed. Is that really the one we've got next? I want to keep these in order. Yep. We're coming back to... okay. We have a problem here. Inclusion, exclusion. Think about it for a moment. Think about how you might approach it. Hint, inclusion, exclusion. It's not quite that easy. But you're the first person to say something and get us started. Thank you. We're thinking counting, that's what I like. All right, more thinking. You see that? Okay, that's good. You got us going. We're thinking. Let's have a look. I'm going to use inclusion-exclusion. It's not always obvious what you should use for a counting problem, but there is a hint here. I'm going to start with a couple of sets. I'm going to have, I might call them P1, P2 and P3. That would be a nice way to do it. So let's let P1 be the number of ways of leaving nothing in pigeon, of doing this, I'll say, of doing this, meaning putting the 5 folders into 3 pigeonholes, of doing this and leaving pigeonhole 1 empty. Okay, that was an essay and a half, wasn't it? Okay. And funnily enough, I'm going to have P2 be the number of ways of doing this, leaving pigeonhole 2 empty, and P3 be the number of ways of doing this, leaving pigeonhole 3 empty. Well, I've certainly got some sets and I can play inclusion-exclusion with this, but will it do anything for us? Let's think for a moment. What's P1 intersect P2? That's the number of ways of doing this, leaving pigeonholes 1 and 2 empty. And the same with P1 intersect P3. That's the number of ways which leave pigeonholes 1 and 3 empty. And pigeonhole 2 intersect P2 intersect P3 is the set of ways, blah, blah, 2 and 3 empty. What's P1 intersect P2 intersect P3? The ways of leaving all of them empty. But here, what I'm looking at is the number of ways of putting the 5 folders in the 3 pigeonholes. So it's the empty set, because the folders have to go into a pigeonhole. It's okay to leave 1 or 2 holes empty, but you've got to have them somewhere. So it's actually the empty set, because you can't leave all 3 pigeonholes empty. The folders have to go somewhere. What has this got to do with the question? The question says, in how many ways can we do it so that no pigeonhole is empty?
So we've got to figure out how much all of that is and then take it away from the total number of functions.
That's right. Let me draw a picture for this.
So are we trying to find like all the times where this one that's left empty and then kind of remove those from?
Yes, that's what we're doing, yes.
Right.
Yes, that's right. So the answer is total number of ways, all ways of putting folders in pigeonholes minus the number of ways which are wrong for this, the number of ways in which 1 or more pigeonhole is empty, which is P1 union P2 union P3. So we're coming at this a little bit indirectly. We're saying, let's look at all the ways of doing this, and then we'll subtract off those that don't do what we want. We'll subtract off all those that leave 1 or more pigeonholes empty. And to leave 1 or more pigeonholes empty means it's somewhere in these sets. So it's P1, P2, P3, all in there, represented in there, are ways of doing this where 1 or more pigeonhole is empty. P2 is empty, P1 and P2 are empty. Oh, there's nothing in the middle there. P3 is empty, so on. Now, this might look like a little bit a long way around, but this is it's not quite a straightforward question, so we have to sneak up on it from behind. Okay, in how many ways can this be achieved? Well, we should answer this, shouldn't we? And now that I've used my piece of paper, I will get out another piece of paper, and so we can write out the whole answer. That's the learning guide. I don't want to write on that. I don't think I do. In here is, swear that I had a piece of scrap. Oh, what's that? Oh no, that's a lovely visual proof of something. Oh, here's my paper. God, I had some scrap paper.
So is it only like the intersections, but not like the middle intersection, or am I thinking about it?
All right. The thing is, there's nothing. We would subtract that off if there was something in there, but there's actually the number of ways of leaving all 3 pigeonholes empty is none. You just can't do it.
Yeah, but like, oh no, but like, I was saying like, is it like all the intersections except like the middle? No, don't worry about it.
It's
Still at the middle, it's just the middle happens to be zero.
yeah. It's we're subtracting off all of this stuff. Where the things are in here doesn't matter. We're subtracting them all off.
Oh yeah,
Okay, we should do this now because it's actually a lot easier than it looks. It's less work than it's less work than our example with the Mandarin, Arabic, and Japanese speakers because there's only a few different set sizes. Number of ways? What's the number of ways of putting folders in? Just regardless of anything. Number of ways of putting 5 different folders, it says different there, into 3 different folders into, this is illegible, sorry, into 3, and I will stress different pigeonholes. Okay, how many choices for the first folder? Yes? What? 5 factorial? Close. Get an egg. No, I want you to actually get it. I don't want to hit you in the head. Okay, is that right? Is 5 factorial right? Is it close? We're getting there, all right? So what would you do it to make it better? It is?
Well, hold on. Do you mean different pigeonholes as in like the end goal where we've got
Well,
no pigeonhole empty? What do you mean by number of ways putting 5 folders into 3 different?
okay, imagine I've got 5 folders.
Yeah.
They're labelled Jane, Joe, Mary, Sue, whatever assignments. Then I've got 3 pigeonholes, Leanne, James, Charles. And I can put James in one of those, and then I put John's in one of those, and then I'll put, yes? 3 factorial?
3 to the 5.
3 to the 5.
5 factorial of 1 to the 5.
I wonder what your exams are going to be like.
Like the question,
All right, you're all sort of around the right thing.
do you mean different pigeonholes by we're already right now discarding any scenarios where, for example, all 5 go in the same pigeonhole?
Oh, no, all 5 can go in the same pigeonhole. I just want everything at the
We're
moment.
actually looking for the number of ways of putting 5 different folders into 3 pigeonholes.
Yeah,
Not 5 folders into 3 different pigeonholes.
5 different folders.
Into 3 pigeonholes.
Into
It could all be the same pigeonhole.
Oh, all right. I guess what I mean is, if maybe I'm all right. The
In this
pigeon.
case, it would
There are
be-
3 pigeons. I mean, they are 3 here. They're labelled Leanne, Charles, and James. So
And in that case, it would be 3 to the 5.
okay, and you.
Is it 7 choose 5? Is 5 into 4 into 3?
Okay, I am really looking forward to marking your tests. Okay, let's think about it. First folder, it says Jane on it. How many choices do I have as to where to put that folder? 3. All right, I'm going to put it there. Right, that's 3 choices. Second task, I've got John's folder. How many choices do I have?
3. 2. 3.
I'm just looking at the number of ways with no restrictions. Number of ways. All ways. No restrictions here. This is the total. No restrictions here. Okay, so, right, so there's 3. So we've got 3 times 3. Task 3, Joe's folder. How many choices?
3.
And the 4th folder? And the last folder? 3. Right, so it's 3 to the 5th.
In other words, trying to find the total number of functions.
Total number, that's right, total number. Okay. Now, what we've come across here is something that it makes counting problems really quite hard because you've got to work out exactly what it is you're counting and then you've got to communicate it. And that can be really hard. Like if someone says, Leanne, I want to know how many times blah, how many lines of code or whatever, how many times through this loop or whatever some program does. Got to make sure you know exactly what happens. And that means often I'd have to interrogate them so I really know what I'm counting. So, and that's what we're doing here. So hopefully you've sort of a bit of backwards and forwards and you've got a better idea of what we're actually counting here. And that's often necessary. And when you're doing a question yourself and you can't argue with everybody around you in a test or at home, you know, you might not have anyone to argue with apart from the cat and the dog, but that's okay, they'll join in, they'll love it. So you can argue with yourself. I do that if I'm stuck with a problem like that. I think, all right, what's the argument this way, that way? And I usually work it out. Okay, so total number of ways is 3 to the 5th. Okay, but a lot of those are not the ones we want to answer the question because some of those will leave a pigeonhole empty and we don't want any pigeonholes empty. Okay, and this is the number of ways that leave one or more pigeonhole empty is P1 union P2 union P3. So I want to work that out and I want to subtract that, the bad ones, from the total 3 to the 5th. Okay, P1 union P2 union P3 equals, oh dear, I don't know what, let's, P1. What's the number of ways of putting folders in pigeonhole but leaving pigeonhole 1 empty? So there's pigeonhole 1, it's labelled Leanne. You're not going to put any of your folders in there, you're going to put them in the pigeonholes labelled Charles and James. How many ways do you have of doing that?
2 to the 5.
2 to the 5, because first folder, 2 choices. Second folder, 2 choices. Right, 2 to the 5th. So that's the cardinality of P1. And it's the same for P2 and P3, because P2 is just where you avoid the second pigeonhole, and P3 is where you avoid the third pigeonhole. So that's also equal to P2 and P3. So P1 union P2 union P3 equals 3 times 2 to the 5th. That's the P1 plus P2 plus P3 bit. There. Now I'm going to subtract off, oh dear, what's P1 intersect P2? I've got my 5 folders. I'm not going to use the pigeonhole named Leanne. I'm not going to use the pigeonhole labelled Charles. I've just got 1 pigeonhole there. How can I put my 5 folders into the pigeonhole? There's one way of doing it. They all have to go into the one labelled James because I can't use those 2, right? So that equals 1, and that's the same argument for P1 intersect P3 and P2 intersect P3. So because of that, I've got minus 1, minus 1, minus 1, which is minus 3. And we've noted that P1 intersect P2 intersect P3 has no elements, because if I've told I have to put my 5, in how many ways can I put 5 folders in 3 pigeonholes if I'm not allowed to use any of those pigeonholes? Well, I just can't do it. So there's none. So, and then at the end, the third is plus 0. So you see, it's instead of writing 2 to the 5th plus 2 to the 5th plus 2 to the 5th, it's just 3 times 2 to the 5th, because it's that plus that plus that. And then it's minus that, minus that, minus that, which is minus 1, minus 1, minus 1. And so there it is. So what's 2 to the 5th is 32, 96, 93. Is that right?
Yes.
Okay, so the answer to our question, let's go back to our question. Aha. Back to our question here. The total number of ways is 3 to the 5th, which is, I'll write that out, 3 to the 5th, minus, and we got the 93, equals whatever the answer is. That's a calculator question, and I'll leave that to you. Okay. Now, the second exercise here is exactly the same. Think about it. Do you agree that it's really the same question?
Yes.
It is. It's the same question in disguise. So the answer is the same. That's actually 150. And the answer here is 150 because it's really the same with the same argument. Now let me convince you of that because some of you might not be convinced. Instead of having 5 folders, I've got 5 letters. A, B, C, D, E. A, B, C, D, E. And I want a function from there to 1, 2, 3. Now, instead of putting a folder into a pigeonhole, I'm going to send an element of the domain to an element of the codomain. So putting Joe's folder in the first pigeonhole might be like mapping A to there. I had 5 things, 5 folders, which I had to send to 3 things. Here I've got 5 elements, which I'm sending to 3 things. So it's really the same. It's just in disguise. So what you might like to do to see if you understand this is to rewrite the answer to this, which is on the various pieces of paper here, which hopefully has been recorded, and rewrite it in this context, because the numbers are the same, the answers are the same, the reasoning, it's identical. It's just instead of folders, you've got elements. And instead of putting a folder in a pigeonhole, you're sending an element of the domain to an element of the codomain. Does that make sense?
Just to quickly go that one, when we are writing down, sorry, P1, P2, and P3 are going to correspond to, they're essentially just
P1 with set of functions that don't send anything to 1. That, or you could say don't, I'll say don't send anything to 1. I think that might be. And so on. So instead of don't put a folder in the first pigeonhole, don't send an element to 1. Okay. Are we doing? Yes, 4 sets. We could do colouring in with 15 colours, but we're not going to. But the pattern is the same. The pattern is exactly the same here. Look at what you do with inclusion and exclusion for 4 sets. To find the cardinality of the union of 4 sets, you firstly take them sets themselves, add up the cardinalities. Then you subtract what you get when you take the intersections of pairs. Now, there's quite a lot of possible pairs. There's 6 possible pairs, but you consider the various intersections, their cardinalities, and subtract the lot.
Is there a nicer way to write that, like using...
Yes. Do we write it on the... Is it written? Do we write it? Did we write it? Did we write it? Maybe I will... Oh, yes, it's... It is written a couple of slides over. You might not like it. It's like that. There.
Beautiful.
You might like that.
Because I imagine once you start getting some bigger things, writing down, it just gets so long that you just go.
Yep. Yeah, that's why you'd write it like this. The union of n sets, you take the sets themselves, their cardinalities, and add them up.
Yeah.
You take the pairs, the intersections, add them up, and then subtract the lot. You take the triples, the cardinalities, you add them up and add them, and then you subtract, and so on.
It's an alternating sum.
It's an alternating sum, that's right. Yes. Yes, so that's a good question. Have I given you an egg yet?
No.
Oh, well, you need an egg then, don't you? You really do need an egg. I think the people in the front few rows are getting more eggs than those people up the back. I like you people up the back. Maybe you should come down and get an egg later. All right, so pattern. Make sure you know the pattern. After you've subtracted the pairs, you look at all triples, intersect, work out the cardinalities, and add them. And then you take all four, subtract. So you see, add, subtract, and that's the pattern for 5 sets, 22 sets, 553 million sets. So that's inclusion, exclusion for 4 sets and the same pattern for more. Yes? Yes. That was this one. Yes. These.
Is it like 3 to the power of 5, 243, the top one 2 to the power of 5 minus 92, just what's that?
Yes, this you will also end up with a 3 to the 5 minus 93, and you will get 150. Yes, you'll end up, those numbers will be the same. Yeah, the working will be the same, the numbers will be the same. Yes, yes. I haven't given you an egg yet, have I? You need an egg. Okay. That's okay. Oh, derangements. I love derangements. It's such a nice word, derangement, isn't it? It sounds so deranged. Okay. A derangement of something is where you reorder them, but nothing is where it was. Nothing is where it was. So here's a question about derangements. My friend Yan knocked over my spice rack, and let's say Yan then put all the jars back in the spice rack, but so that every single jar was in the wrong place. The number of ways of doing that so that every single jar is in the wrong place is the number of derangements. A derangement of something means that you have everything has moved. Nothing is where it was before. Okay, so a permutation is just a way of rearranging 1 up to n, where some things might be where they were before and some things might not. But a permutation is a derangement if the ith thing is not I. So you might have started with 1, 2, 3, 4, 5, 6. If it's a derangement, the first thing will not be 1, and the second thing will not be 2, and the third one will not be 3. Everything will have moved.
So it wouldn't be a derangement if everything was different except for 2 was still in the 2 spot.
That's right, yes, yes. Everything must be different. That's right. Now, here's an amazing little, this really is amazing when you first see it. The number of derangements of n objects is the closest integer to n factorial over e. Now, how many of you are aware of the natural constant e? As in, some of you are. E is approximately equal to 2.71828182845, and so on. Goes on forever. It's a really important natural constant, perhaps the next most well-known one after pi, pi 3.1415926, etc., etc. So that's a natural constant. It's a really important one. And the number of derangements is the closest integer to that. And that just sounds bizarre, but amazing, doesn't it? That you can see E in this. Anyway, I'm going to show you why. Most of you probably won't know all the maths, but you can at least admire it as it goes by. Okay. And oh yeah, E is that the base of the natural logarithm apart from a whole lot of other things. Right. So is that the next? Am I out of order? Because that was, I want page 12. I want page 12.
Yeah, that's the next page.
That's the next page, right. So this is the proof of that amazing fact being the one we just stated here. But on the way, we get to the exact number of derangements, and then we show this bit about the closest integer. Okay. Now, the second half of this proof does use stuff from Maths 1B, which I suspect none of you have done. Has anybody here done Maths 1B? No, I didn't think so. Okay. But the first bit is stuff that belongs here in discrete maths. So the first bit you'll understand, and the second bit, I've just got to show you roughly how it works, just because it's also useful, but it's just nice to see. Okay. Let X1 be the set of permutations of our set N that fix 1. What that means is that you started with, you've got your 1, 2, 3, etc. up to N. And a permutation that fixes 1 means 1, it's like it's glued in its spot. Doesn't go anywhere. Now, the other numbers might go somewhere. They might stay where they are. Who knows? They do all sorts of things. But if 1 is fixed, that means 1 is, imagine it's glued in its spot and so it couldn't move. All right. So X1 is the number of permutations that leave 1 where it was. You can do anything with the other numbers. And 2 is the number of permutations that leave 2 where it was, and so on. Now, X1 union X2 all the way up to Xn is the set of permutations that keep at least one element where it was. So these are all the things that are not derangements. A derangement leaves nothing where it was.
That's pretty similar to what we were doing, right?
Yes, it is. You spotted that. Look, you do deserve an extra egg for that. See, I know that most of you are thinking that, but you're sitting there very quietly. Yeah, he's a loudmouth. Yeah. Actually, I shouldn't reward that. I was told once not to. Someone complained. They said you shouldn't encourage those people. But no, it's a really good comment. This is so like what we just did. So like what we just did. Okay, so X1 union X2 union Xn, the permutations in there have left at least one element where it was. If it's in X2, then 2 hasn't moved. If it's in X2 and X4, then 2 and 4 haven't moved. These are all the ones that are not derangements. They're the ones we don't want to count. But if we can count them, then we've got our answer. The number of derangements, Dn, the number of derangements is all possible permutations, and we know there's n factorial permutations, go back 2 weeks, n factorial permutations, all permutations minus the ones that are not derangements, and that's our answer, okay? So if we can work out this, we can subtract and work out the number of derangements. And this is going to be just like what we did in the previous question. By inclusion, exclusion. Okay, so here's we get this. Now, this might look a bit sort of, lots of notation, but it's just saying what we did. You take all the sets themselves, work out their cardinalities and add them all up. And then you take the pairs, intersect them, cardinalities, and subtract them. Triples, add them, and so on. That's just what we saw. And that's the general pattern. So we just have to work out each xi. What is the order? Let's start with x1. If I've got n things, and I'm looking at all permutations that leave 1 where it is, all right, 1's not moving, but 2 up to n. What are the number of permutations of 2 up to n? Very close, almost perfect. We've got n minus 1 elements, so it's n minus 1 factorial. Yes, so that's it. Right idea. Now, it doesn't matter whether it's x1 or x2 or x whatever, does it? They're all, it's the same argument for each of them. So each of these is n minus 1 factorial. How many of them are there? Well, there are n sets. N choose 1 is n, so it's n times n of these. It's n lots of those, so that's how we get that there. All right, let's do a couple more terms. Let's look at x1 intersect x2. To be an x1 and x2 means 1 stays where it is, 2 stays where it is, but all the other numbers can go anywhere. So how many permutations are there from all the numbers of 3 up to n? N minus 2 factorial, because there are n minus 2 things that might be moved, that can be moved, and so it's n minus 2 factorial. And so that's why this here, that's n minus 2 factorial. Now, in how many ways can we get a pair of sets? We've got n sets. How many pairs are there? What's the number of ways of choosing 2 sets from n sets? N choose 2, and that's why the n choose 2 is there, because there's n, we see n choose 2 of those n minus 2 factorials. And so it continues. When you've got a triple, you're looking at the number of permutations, which leave 3 elements in place, but the other n minus 3 numbers, you're just looking at all permutations of those, so that's n minus 3 factorial. That's why the n minus 3 factorial is there. And how many ways are there of choosing 3 sets from n sets? N choose 3. So that's why that's there, n choose 3 times. And because it's our inclusion-exclusion, we go minus, plus, minus, and dot, dot, dot. We just keep on going. That's it. That's our number. So you can leave it like that, or because there's a pattern here, you can note that we've got all n choose whatevers, n choose 1, n choose 2, n choose n, all the way up. So we can say each term has the form n choose k of n minus k factorial. And then to get the sign right, so it's plus minus 1 to the k minus 1 assures us that we add on those terms and subtract on those. So you can write it like that, or you can write it like that. You might find it more friendly like that. I'd choose it like that. Okay? But then, because n choose k, you know what that is. N choose k times n minus k factorial. You know that n choose k is n factorial over k factorial, n minus k factorial, and then we're multiplying this by n minus k factorial. Things that cancels. And so instead of writing this, we can just write the n factorial on k factorial. So that, that is just equal to that. So that simplifies nicely. And then the other thing you can do, and you'd see this if you write it out, because you've just got an alternating sum of these. Let me write out the first few terms of this alternating sum, because it's n factorial over 1 factorial minus n factorial over 2 factorial plus n factorial over 3 factorial minus n factorial over 4 factorial. And about here we get really bored. There's a common factor of n factorial in there, isn't there? So that's what's happened there. That common factor of n factorial has been taken out the front, and we've just got this. Each term, if you take the n factorial out the front, you've just got something really simple left. You've got your pluses and your minuses and your k factorial on the bottom. And anyone who has ever done a Taylor series expansion of E will recognise that. And that's where the Maths 1A comes in, and that's where I'll just show you what this stuff is, because it's amazing, but it's got nothing to do with this subject, and you don't have to know. But this gives us the number of derangements now. It's n factorial minus that, because remember on the previous slide, the answer was n factorial minus this big union. So it's n factorial minus this big union, which you can write in a slightly nicer way, because actually n factorial fits this. You can take out the n factorial out the front, and that 1 fits the pattern. So instead of going from 1 up to n, you can go from 0 up to n, because the 1 there actually fits the pattern. It's just, turns out to be so beautiful. Okay, so that's it. And you'd see that if you didn't use the sigmas and you wrote that out, you'd just see it straight from your term like this, your dot, dot, dot. Okay, so now I want to just whiz through the next few slides just to show you, just to give you an overview of how this amazing n factorial over e stuff comes in, because it really is magic until you see it, and then you know it's not magic, it's for real. Okay. You probably know that you can, well, pi, e, numbers like that, which with decimal expansions on forever, we use approximations for them, and there are various ways of approximating those numbers. One of them is that we have various series which converge to those numbers. And for e to the power of x, e is 2.71828, etc. E to the x is a number that's going to go on with decimal expansion forever, but it's actually equal to this sum, 1 plus x squared on 2 plus x cubed on 3 factorial, etc. It's this sum here. There's a whole lot of maths behind that, but that sort of thing is really useful. And it might be it's the sort of thing that's useful to see. It's useful to know that these expansions exist. These are really good series. They converge quite fast. So if, for example, you were designing a calculator and, I mean, if you want to, you know, your calculators, you press sign and there's a button for E and numbers like that. It's series like this that the calculators use to calculate E, to calculate signs of numbers, to calculate e to the x, to calculate log of x. There's series for lots of things, and if you take enough terms, you get an approximation that's good enough. And that's all I want you to know about that these things exist is nice. But that means that I'm going to skip all of this stuff. What this says, basically, is that this is a good approximation. So I'm going to skip this because nobody's done 1b, and I don't want to go into this. But you also study how good an approximation it is. It's good. Right, we're on to the next slide. I mean, one day you might come and be lucky enough to do some of this stuff, and then you can spend time going into how good the approximation is. But e to the thing is, right back up the top, if I put x equal to -1 here, e to the -1, if x equals -1, we're looking at e to the -1, and we get that it's, if x is -1, that's 1 minus 1 plus a half, which is 2 factorial, minus 1 on 3 factorial, plus 1 on 4 factorial. Oh, that's the sequence we had, wasn't it? That's our one from our inclusion-exclusion. That's it. It's e to the -1, except we stop at a certain point. Okay, but e to the -1 goes on forever. What this means is that for our, which was our Pn? Oh, Pn, that's right, that's the power series, that's the whole, there's the power series. If you stop after m terms, that's the partial sum of your just n terms. And that's what we were looking at, p of -1. Because if you stop after a certain point like we did, then what we're really looking at is p of -1. Okay. So p of -1 is very close to 1 over e. That's what the previous slide said. It said that if we, e inverse, which goes on forever, if we just stop at the first few terms, that's a good approximation. And that basically gives us to us, because that says we knew that we had n factorial times that alternating sum, and that alternating sum is very close to 1 over e. So I'm going to stop to the last line and say that what we have is very close to the sum, the whole thing for n factorial over e, because e is just got lots more terms than our sum, but those terms get very, very, very small and we can ignore them. And it turns out that the approximation, it's a good enough approximation to say what we want is actually the closest integer to this value. So I'm skipping a whole lot of stuff here, which is not examinable. It's only the derangement and the inclusion-exclusion stuff that is part of discrete maths. This was just a bit of extra to show you that you actually get the magic. Because if you do want to find out the number of derangements, the easiest thing to do is to get your calculator, press n, put in n, press factorial, divide by e, your calculator has e, and just round to the closest integer. And that's it. You don't even have to do the plus minus, plus minus, plus minus, plus minus stuff. Once you know that, you can calculate the number of derangements so incredibly easily. Isn't that amazing? Isn't mathematics just fascinating? Just fantastic? Okay, all right. So I've sort of skipped a lot of the proof because the stuff that you haven't seen before, I just wanted to show you it exists. That's all. Okay. This is useful. I remember doing this. I was at a wine tasting many years ago with a bunch of statisticians and applied mathematicians. And what we were doing was trying to, the wines were all, the labels were covered, and we were looking at the probability that we'd all guess the wines, every single wine wrong. Because we had, say we had 8, these guys were serious drinkers, I wasn't, I came along for the bread and cheese. But they had 8 glasses in front and 8 bottles, and you didn't know which wine corresponded to which bottle. The bottles were labelled A, B, C, D, etc. The glasses 1, 2, 3, 4. This is serious. This is what they did every month. It was the applied maths wine tasting. It was a lot of fun. Anyway, so Malcolm was a statistician. He says, all right, let's work out the probability that we all, or basically that we get every single wine wrong. I reckon that's the 87 claret or whatever, and it turned out to be the something else, And I think a lot of us did get it wrong. I didn't have a clue. I was doing it by random. Anyway, so what's the probability of that? Say, all right, you pick a permutation at random, like I did. I guessed what wine was what at random because I didn't have a clue. The probability that it's a derangement is approximately 1 over e. The probability that everything is wrong is 1 over e. And the larger the number of things you're doing, like if you've got 30 wines instead of 8 wines, it's a better approximation. And that's whether you get drunk or stay sober. It's approximately 1 on E, which is about 0.367. It's interesting, isn't it? All sorts of fascinating stuff you can do. But anyway, we have one more topic to cover. Okay, so we're leaving our derangements behind. We're not deranged anymore. We're going to take a breath and go back to binomial coefficients, except it doesn't say binomial, it says multinomial instead of bi. So we've gone from bi, which is 2, up to many. First question, how many words can you form with the letters of bad? The answer is there. There's 6 of them. All right, let's change the question. What if we look at the letters of dad? Because 2 letters are the same, we can only form 3 words. The answer's different. Okay, because if I swap that D and that D, I don't see any difference. It's the same. So we actually get half the number. Okay, because there's 2 Ds. All right, so that's the sort of problem we're going to look at, except we're not going to start with something like dad. We're going to work with Woolloomooloo. Because a few years ago, when I was setting a test on this, a friend of mine said, let me find some other name places apart from Woolloomooloo. So he sent me Bullamakanka and all sorts of lovely places with lots of letters and lots of repeats. How many words can be formed using all the letters of Woolloomooloo? It's not 13 factorial because there's lots of repeats. And again, this is done with pretty colours because James is great. So you can see if I swapped the O's with each other or swapped a couple of L's, it's the same thing. So we're going to get a lot less than 13 factorial, many less. Well, we're going to look at finding all the ways of arranging the letters of Woolloomooloo by breaking this up into 4 simple tasks. For the first one, we're going to place the O's. So let's say we're going to do this again, we've got our 13 places and we've got, how many O's do we have? we have 8 O's. There are 8 of these things, 8 of them. We're going to place the 8 O's. Well, I have 13 places, and I want to choose 8 of them for the O's. In how many ways can I choose? 8 places from 13 for the O's. 13 choose 8. You are all so good. Isn't that great? Actually, I think I need to give some eggs. People up the back, would you like some eggs? Someone from the back, come down and get a couple of eggs. I'm not going to go up there. You've got to come down. Up the back. Doesn't anybody up the back want an egg? All right. If you're halfway up the back, come down and get an egg. Whoops. All right, give it. Make sure you give it to a few people. Here, give it to a few of your friends up there. I know, everybody is so lazy. Make sure everybody up, or a few people up there. I think there's another one up there gets eggs. And the rest of the eggs are for you people down the front. All right. Okay. 13 choose 8. You're right. You are all so clever. Because we're choosing 8 different places. I can't choose the same place twice because the idea is to put each O on a separate place. I'm not going to put another O there because that's taken, so there's no repetition. And it doesn't matter what order I choose it in. It just matters that I end up in some order with 1, 2, 3, 4, 5, 6. Good grief, there's a lot of O's. 8 O's down there. I just need to end up with 8 O's. It doesn't matter in which order I write them. So it's no repetition, unordered. So it's 13 choose 8. Good. Task 1 is done. We can tick that off. L's. All right, there are 3 L's. How many places do I have left to use for the L's? 5. In how many ways can I choose 3 of those 5 places for the L's? 5 choose 8. You are so good. 5 choose 3. That's right. So let's do that. So I'll just put L, L, L. Okay, that's task 2 done. I come back to, let's do a W. Oh, we've only got 1 W. There's only 1 W, isn't there? 1 W. In how many ways can I choose 1 place from 2 for the W? 2 choose 1, which is 2. That's right. So we can put W in. And finally, it's 1 choose 1 for the last letter, M. So we can do this quite easily, can't we, using what we know? Yes. And the answer is 13 choose 8, 5 choose 3, 2 choose 1, 1 choose 1, multiply them all together. And if we write this out, notice that it works out quite nicely. That 5 factorial cancels with that. That 2 factorial cancels there. And that 1 factorial cancels there. And just to continue this pattern, I'm going to get rid of that 0 factorial because 0 factorial is 1 anyway, so it doesn't make a difference. And the answer is 13 factorial divided by 8 factorial, 3 factorial, 1 factorial, 1 factorial. And that is nice. There were 13 letters in total, 8 places for the O's, 3 L's, 1 M, 1 W, 1 M. 8, 3, 1, 1. So it works out nicely. So if I was to give you Bull and McCanker, you'd be able to write down the answer now quite easily. Now what we have, this number here, is in some sense a generalisation of the binomial coefficient, and it is called the multinomial coefficient. So it's n factorial, and you've got all those numbers there. Okay. A multinomial coefficient, you have natural numbers, 0 or greater, and you have a whole lot of numbers there for which, that's true, those numbers must add up to n. You can have as many numbers there as you like. You can have 1 number. Well, yeah, as long as it adds up to n, that's fine, meaning it has to be n. So you have natural numbers, you have this number, and those numbers add up to that, and that's what it is. And that's the number we saw as an answer to our problem of arranging the letters of Woolloomooloo. And given the name, you might guess multinomial coefficients that it's got something to do with coefficients of something, which is probably a multinomial, even if you don't know what that is. So, for the last couple of slides, I'm going to tell you what this multinomial stuff is. But firstly, let's note that a binomial coefficient is actually a special case of a multinomial coefficient. It's just that. Two numbers. Those two numbers add up to n, and the formula for that is exactly that, which is exactly what n choose k is. And then what we discovered here, and you can do this because we've done it with Woolloomooloo, and you just break it up into tasks, and it's something we've done for a few weeks now. You will probably agree that the number of, if you've got n objects, and there are k1 of type 1, k2 of type 2, etc., like you might have 8 O's and 3 L's and so on. The number of ways to arrange those objects in a row is, well, it's n choose k1 times, and you keep going as you did with the Woolloomooloo, and you simplify it and you get the same number in the same form. And that's the notation we use for that. So that's just Woolloomooloo in general. So you could do how many words can be formed by using all the letters of Arch Chronicler. And I mean, that's just a matter of counting how many letters there are. That's the hard bit. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it's a multinomial coefficient, 14 choose something. And I actually wrote this one out because we're not going to do it. I swear I've got it somewhere. Maybe I lie. Do I? All right, I lied. I haven't got it. Because I'm sure I'm going to get it wrong if I write out. How many C's are there? C's, 3. Okay, so we've got 3 C's. How many R's are there? 3 R's. How many H's have we?
2.
I think we've got 2 H's. All right, so we have A's. How many A's? Do we have 1 A? An O? An N? An I? 1 I? An L and an E. Okay, so it's 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, I got that right. So it's going to be 3, 3, 2, 1, 1, 1, 1, 1, 1, 1, 1, 1, with commas between them. Okay, which you can work out. Okay, so that'll be the answer. But if you think of it in tasks, you don't have to remember the definition of a multinomial coefficient because it's just using what you know from the last few weeks. Yes?
Once you get used to it, you don't really worry about the ones, do you?
No, if you're just writing down the answer, when you're using the multinomial coefficient, put them in because the sum of the numbers there must equal that. But yeah, when you're writing out the answer, yeah, they're not there. Yeah, when you write it out as factorials, they're not there because multiplying something by 1 doesn't affect it. Here we come to the multinomial theorem. It looks like the binomial theorem. It's exactly the same as the binomial theorem, except that instead of having 2 things here, you've got m of them. You've got many of them, multi. That's why it's the multinomial coefficient, multinomial theorem. Now, if you had 2 of these things here, if m was 2, it is exactly the binomial theorem. And what it says is pretty much what the binomial theorem says, except it's a bit messier in places, but it's really saying the same thing. Because you've got lots of different things here, x's, you've got all sorts of possibilities here, lots and lots of possibilities. You've got your first x1 to some exponent, x2 to some exponent, and so on. And your exponents must add up to n. And you've got all possibilities. So here is a slightly different way of using the sigma sign. What we're putting under sigma is the conditions of the terms we're adding. It's not as simple as start at 0 and go up to n. We're saying we add every term that has the k's adding up to n, and for which our k's are natural numbers, meaning whole numbers greater than or equal to 0. You've got to find all possible k1, k2 up to km, which are 0 or greater, and which add up to n. So if James is in a bad mood, the final exam question will probably have something with a big N and lots of things here, and you'll be there for half an hour. If James is nice, he won't do that to you. So let's use this to expand a couple of things. And, the proof. We don't have time for the proof today. If you want to, we can talk about it next week. But we don't have time today. Expand x plus y cubed. I think we might come back and talk about the last couple. Subjective here. We won't do all this today. We'll come back to the last slide or two next week because we're just running out of time. But let's expand this. We should at least, we've seen the theorem, let's use it. It's the sum. And I'm looking for all K1, K2, and K3, because in this case I've only got 3 terms, m is 3, such that K1 plus K2 plus K3 equals, that's my n. n equals 3. Of terms 3, K1, K2, K3, A to the K1, B to the K2, C to the K3. Now, you actually don't need the multinomial theorem here because you can just multiply that out anyway. You might like to do that to check that this answer is working out okay. So we've got terms. We're looking at all numbers in n. So there's a few possibilities. There's 3, 0, 0. So I've got 3, 3, 0, 0. A to the 3, B to the 0, C to the 0. So they disappear, and that actually is just A cubed when you simplify it. Plus, 3, 2, 1. 3, 2, 1, 0. A squared, B to the 1, C to the 0. Plus. Okay, you get the idea? Do you want to write all these out now?
Yes. There's always 3 on the top of the multinomial coefficient.
You've always got your 3 here. You've always got the same thing up there.
Right.
How many people want me to write these all out? I'm going to write down another 2 just to keep... There aren't actually that many. 3, 2... No, because if you're looking at numbers that add up to 3, you've got 3, 0, 0, 0, 3, 0, 0, 0, 3. You've got 2, 1, 0, 2, 0, 1, 1, 2, 0, 0, 2, 1, and 0, 1, 2, 2, 1, 0. So that's all the possibilities down there. Can you read those? No, you can't because they're half off the screen. So you've only got that many possibilities. I haven't got room to write all those down anyway. Let's do 3, 1, 2, 0. That's A to the 1, B squared, C to the 0 plus. All right, now I'm going to put ... because I will run out of room. It's not hard to do. If I had a whole space here, I could fit them in, but there's quite a few terms. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. That's all. Not many. Okay. And then we can find the constant term here. Look, I think we're out of time, maybe we'll come and play with this a little bit next week, because I know that I really appreciate that you've stuck around after your test. I don't want to take any of these eggs with me, so there's a keen. I like people who are keen.
Thank you.
You know, another one. People in the front first. People in the front first. Now, come on, you guys. Here, you haven't had an egg, have you? No, you're all right. You've had it. Oh, you had an egg, haven't you? One. All right, come on. Now, here. Egg. Have you already had an egg? No more. Do you want an egg? Anybody want? Who wants an egg? Yeah, you need an egg. You need an egg. Okay. Thank you, everybody, for coming. I hope to have your tests this time next week. That's my aim. I won't promise, but I think it's highly likely. So, see you next week.
Thank you for that.
Pleasure. It's fun stuff. There's some amazing stuff in there, isn't there?
Especially with different slots and different hours.
Yeah, it's nice, and you can do so many fun things with them. Yeah, it's good.
Good question about practice the next couple of weeks. So